And we continue with our next session, and this session will be given by Dmitry Soshnikov. He is a consultant and Yandex Cloud Service, and also he is an associate professor at High School of Economics. So please welcome him. And let's start.
Thank you so much. You've just heard an excellent introduction to large language models from Piotr, and I will continue on this topic. I will develop it into the area of multi-agent systems. Multi-agent systems is a kind of popular buzzword nowadays. So let me start by continuing the idea of retrieval augmented generated systems. First of all, you've seen in the previous demo large language models being used locally from the Jupyter notebook, and that is good for small language models, but for really large language models, it's in most of the cases it's much better to use the API, to use them in the cloud, because you don't have to worry about the speed, you don't have to worry about compute that you need to run large language models. And that's why I'm here. One of my roles is to present Yandex Cloud, a Russian cloud provider, which you probably most of you know. And as part of the school, you would have access to Yandex Cloud, so you would be able to use, first of all, computing resources in case you need to do some kind of fine-tuning or model training, and you would be able to use large language models themselves. In Yandex Cloud, there is a number of language models available, starting from Yandex GPT, our own model, which is based on Qwen, and which is fine-tuned for Russian language, and latest versions of Llama and Qwen original versions. You can use them. So in order to develop, since we are going to talk about agents, right? An agent is some kind of entity which knows about some topic. So in most of the cases when we talk agents or assistants, we mean retrieval augmented generation. Because there was a question about fine-tuning versus retrieval augmented generation. Fine-tuning in most of the cases doesn't allow you to put new knowledge into large language model. Because large language models has been pre-trained on so much text that you cannot really erase all that memory, right? So large language models will remember anyway what it has been taught before, however much new data you provide. So much more secure way to make sure that the model speaks your data, your information, is to use retrieval augmented generation. To create a retrieval augmented generation system, you can use LangChain. LangChain is a great framework. However, you've seen that it requires certain amount of technical infrastructural problems to solve. Like a simple example, of course, works very well, but in production systems there are questions. What would you, like if you have a lot of documents, how you would index them, how you would handle re-indexing, how you would handle faster retrieval and so on. That's why, because retrieval augmented generation systems, they are very popular nowadays, and cloud providers, they try to find easier way to give to people the easier approach to creating retrieval augmented generation systems. So that's why Yandex has created its own assistant API, which is a special kind of layer on top of large language model to create systems based on retrieval augmented generation and on external function calling, because function calling is the second feature that is very useful for creating intelligent assistants. So what I will show you now, I will, since my talk is titled Multi-Agent Systems Overview and Demonstration, I will do a lot of demonstration. And the GitHub repository with the code that I will be showing is provided here. And the example that I will be showing you is actually So the code I will be showing you is an assistant for selecting wines. So that's why I hope that everybody here is of legal age and you know that drinking alcohol is not good. And having said that, if you are younger than that, please leave the room. I will show you the demonstration. So the GitHub repository that I have shared, it is mostly in Russian because it has been used at some other demonstrations in Russian, but it contains the English directory, and that is the code that I will be showing you today. It has been translated into English. I will be running it locally in VS Code on my own machine, but of course you can run it also elsewhere, wherever Jupyter Notebook is available. So the first example that we will start with just creating the RAG system, similar to the example that Piotr has shown, but in the cloud. To use something in the cloud, you need kind of access tokens or something like that, because whenever you use something in the cloud, somebody pays, right? So if you will be using something as part of this summer school, Yandex pays for that. So you would have access, you would get access to Yandex Cloud, and you would be able to create special API key to use with Yandex GPT and other foundation models in the cloud. So so this code assumes that you have those API key and also folder ID available to you and set in environment variables. So I will not spend a lot of time right now explaining like where to get those. I have shown that there is a pre-recorded video in Mattermost. There is a special separate channel called something computational resources, and there is a link to the video where I talk about Yandex Cloud in general, what it is, and it talks about how to get those access tokens. So in short, just very briefly to show you, access to Yandex Cloud you can get through console.yandex.cloud. That is kind of web console. And here you can create different computational resources. And to get the keys, you need service accounts. And you create a service account which will handle all requests to large language models on your name. So that's very briefly how that works, where you get the keys. And then we also use a library called Yandex Cloud ML SDK, which provides access to all foundation models in the cloud. So that's very nice SDK. You can also use Yandex foundation models through OpenAI API. So you can access them exactly in the way like ChatGPT and most of the other large language models out there. But using Yandex Cloud ML SDK is like if you are not using some existing libraries like LangChain, it's much easier to use this Yandex Cloud ML SDK. So it's just to show you an example, I create this SDK. Oops, sorry. You create this SDK object, you create large language model, Yandex GPT, release candidate last version, and then you say like model.run, which wine is the best with steak, just to start with this wine example. And we will see what LLM knows about matching food and wine. So it recommends more or less reasonable choices. So that is what LLM already knows. So what as Piotr mentioned, if I want to create a chatbot needs to know the previous conversation, right? It needs to keep the history of the conversation. So keeping history of the conversation is handled by this assistant API. So as I have shown in my very beautiful slide here, an assistant is an LLM plus memory, which holds conversation context, plus some custom tools or search tools. So here with Assistant API, we say, okay, I define two functions to create a thread and to create an assistant. It's basically SDK call plus some kind of expiration policy, what to do when it's not active. So I specify like how many days it should stay alive when nobody is talking to it. And then like doing the conversation is simple. I create the new thread. Thread is the memory. Create new assistant, provide it with the system prompt. This assistant.update sets the system prompt. I can say you are experienced sommelier, and so on and so forth. And then I say, hello, which wine do you recommend? I write this information to thread, I run it through the assistant, and I print the result. So that's how like one turn of the conversation is handled. And it gives me like the answer, like what do you want to eat? I need to know about the food first. And then I say I want to eat steak, and since I write it to the same thread, it continues on the previous conversation and provides me with the final answer. Yeah, in frameworks like LangChain, you would basically have pretty much similar functionality. It may require a little bit more playing with the memory, but still it's similar. And then from the thread, of course, you can extract the whole conversation. And then you can delete the assistant and the thread. So that's how Assistant API works. So Assistant API is LLM plus conversation memory. Now we want to add retrieval augmented generation. For adding retrieval augmented generation, you need some kind of documents. And documents, they should be pretty much plain text, because that's what LLM works with. In Yandex Cloud, it accepts different types of documents. It accepts Word documents, PDF documents, Excel documents even, I think. So what it does with them, it extracts text from them behind the scenes. So in practice, it's much better if you do it yourself. Like if you want to implement a good RAG system, I think the best way is to look at the knowledge base and make sure it's good. Often people don't do that, but to ensure the best possible answers, it's much better if the knowledge base is structured well. But you can just throw a bunch of existing documents at this Assistant API and something would happen. Maybe it wouldn't be too bad, maybe you can use it as a starting point. So to do that, you just basically upload files to the cloud and then create an index. So I will, what I want to do, I want to teach this assistant to do food-wine pairing in a better way than it can do now. For that, I have found a table on the internet, a table like this, like a dish and a recommended wine. And it has, this is just first few rows, it has a lot of like different options. So how do I put this into retrieval augmented generation? It is a large table, so it cannot be one chunk. You need to chunk it into parts. And like you can chunk into parts automatically, but that would not be good enough because it would lose the header. The header carries additional information for LLM, right? The header explains you what this table is all about. So it might work without the header, but it's much better if each chunk has the header. So what I do here, I do manual chunking. I select the header, I say my chunk size would be 2000 characters, and I split that into separate documents, which I upload to the cloud using SDK. So essentially, what I do here, I split this table, I upload it, and I get a list of some objects, like 15 table chunks. I have the list of those file IDs in the cloud. And now I need to create an index. An index, like Piotr has mentioned, that embeddings is a good way to do indexing. It is indeed, but if you talk about wines, in many cases, like you might want a specific wine name, like Cabernet from a certain winery. And if you want a specific wine name, embedding becomes not so good, because embedding captures the approximate meaning, and the approximate meaning would be like very similar to all Cabernets across all possible wineries. So in case you have the problem like this, when you need specific model names, like you are creating a support line for repairing something, you need specific model names, a good option would be full text search, like BM25 and those kind of direct searches. You can specify what kind of index do you want, and also you can use hybrid search index type. That is what we will be doing here. We say I want this to be hybrid, I want to combine two indices using this reciprocal rank fusion index combination strategy, and you can guess that there are some other combination strategies available. And we also here, we provide chunking strategy, but we don't need it because we have already chunked our documents. But in case you didn't, you can provide chunking strategy here. So that is what it takes to create an index. And that's basically it. Then you say, okay, I can create a search tool based on that index. And I create an assistant, and I provide this assistant with a search tool. So basically, I say I want the assistant to search each time you have some kind of question. Please search first, and then put that information into the prompt. And then I create the system prompt. Please look at the available information and answer users' questions. So that is what it takes to create the RAG system. And I say, I start a new thread. I say, which wine is best with steak? And let's see if the answer gets better. Are there any wine experts here to tell me if the answer is better or not? Is it better than this one? Looks like it is better, because here in the beginning, LLM just told us, you see, here is the list of wines, and that's it. After what happened, it tells me, like, for this kind of steak, for rare aged steak, for medium well done steaks, and for filet mignon, different wines are good. Why? Because it took this information from the table from two different columns, actually, like two different rows. And we can actually see which fragments of text were used in finding the answer. Here are, how many of them? 5 or 6 fragments of text which were put into RAG context. And there was a question like how to find which one exactly was used. There is no easy way. Like as Peter answered, there are complicated ways, but no easy way. And especially no easy way with the cloud, because in the cloud you don't have access to weights of the model and to activations. Okay, so that was like simple RAG system. Now, what if we want to have a shop with wines and we want to provide the information about the price list? How can we handle this problem? The problem is that, well, of course you can say you had the table of food wine pairing, why don't you just handle the price list using the same approach? Well, it wouldn't work well, because if I ask, like, what is the cheapest red wine available? How RAG system would handle that? I mean, it would find some relevant chunks and provide them to LLM, but there is no guarantee that the whole table would be there. So there is no specific entity who would do like this sort by price and give me the smallest price. Right? So like using querying tables, querying large amounts of data cannot be done using traditional RAG. It can be done using a separate technique called function calling. So function calling is in general very useful technique. And the idea of function calling is that, well, I should show you the slide about the idea of function calling. Actually, I should tell you one more thing before that, sorry. I spoke already about different search types. Yeah, one thing that I want to mention, but I don't have the slide for that, it just came to me, that it's worth mentioning, is that sometimes you need, like in RAG, there are two steps, like retrieval and then figuring out the answer using LLM. In retrieval, there are some tricky things. For example, if I had the previous conversation with the agent and I mentioned something like I said, what is the cheapest red wine? And then in the next phrase I said, what about the white one? It should know that I'm talking about white wines, right? So it should know the context. But this context in classical RAG, it's not passed to the retrieval because retrieval is handled only based on the user input. not the history of the conversation, right? So if you want to handle the cases like that, before passing something to retrieval, you need to aggregate the previous content and do this kind of resolution. So sometimes before retrieval, there is a separate step in reformulating query. Also, after the retrieval, there could be a separate step in re-ranking, like if you have received a number of responses and you want to additionally change the importance of them. So that there could be some pre-processing and post-processing to the retrieval phase. And you can also put that into Assistant API. So now let's talk about function calling. Suppose I want to add this kind of functionality to handle wine price list. So how function calling works? Suppose a user says, like, I want the cheapest Merlot available. What happens next? I pass this to LLM, and I also pass to LLM the list of possible functions that it can call. So I say, okay, there is a special function search wines price list, and there is a function, for example, to add wine to shopping cart. If you want to call any of them, please feel free to do so. And then LLM figures out, do I want to call a function or do I not want to call a function? So how that happens during training, those guys who trained the model, they provided a lot of samples with function calling, and they trained the model to react when it feels that it needs to do a function calling. So function calling is something built into the model at the step of training, at the training stage. So then LLM definitely decides to call a function. Well, sometimes it doesn't, but in this case it should probably decide to call a function. And what it does, it says, I want to call a function search wines price list, and the arguments are the following. The arguments are provided here in the in the schema description. So that's why LLM extracts arguments from the natural text and gives you like everything that you need to do function calling. So it returns you this information. I need function call. Please do something. Then it's my responsibility to handle this, to write some code to do that. And then I pass to the LLM the result, and it gives me the final answer. Right? So let's see that. Let's see how that works in the code. So I would open this kind of price list. It is fictional price list, which I have generated using ChatGPT yesterday. Now, for my function, I need to specify the arguments. Like if you use like raw LLM API, you need to specify like JSON schema. What is the JSON schema of all the arguments and all the functions? In API, in Yandex Cloud ML SDK API, you can just say, here is the Pydantic object, and there are following fields like name of the wine, country, acidity, color, red or white, and what do you want to get, most expensive, cheapest, random, average, and so on. And all of those arguments are optional. So if I just say I want to know how much is the wine, then you would get an empty object. I say I want a function based on this search wine price list object, and I pass this price list search tool as another tool in my assistant. And I also mentioned it in the prompt. I say if there is if the question is about specific wines, wine availability or wine pricing, use function calling. That is just to hint to the model that it has function calling. You don't have to do that, but it helps to specify it in the prompt. So now if I say which is the cheapest wine from Australia, what happens? LLM doesn't return me the answer. It returns me the result with the status tool call. And you see it says the function name is search wine price list. And arguments are output cheapest, country Australia. And that's it. So now what I need to do, I need to handle this function. So I will write a function find wines, which will find the wine in the price list. And here I would handle the assistant run in the following manner. So I first run the assistant. If it requires function calls, I do function calling, and I submit the result of the processing. So that's how it works. And then I submit the result, and wait again for the final result. So that's how it works. So I run this. It tells me processing function call, and gives me the final result, status completed, and the answer, the cheapest wine from Australia, is the following. So that is how function calling works. Any questions? Yeah. I can take a short break while you talk.
Yeah, thank you for this part of lecture. I have a question about the choosing of the right function. How do you think, or maybe you have any experience, is it better to use LLM, as you just said, as you just demonstrated, to decide which function we should call, or just train separate classifiers which you run every time and decide?
Well, I think training classifiers is kind of pre-function calling way of doing it. Function calling is essentially a classifier built into the LLM. Like LLM is trained automatically to handle that. It works well up to a certain point. Like if there are more than 10 functions, it becomes bad. So if there are more than 10 functions, you probably need to restructure your functions. Like you can call a very generic function, and that function can handle further like classification, like further bunch of cases. I think that would be the preferred way. Like if you can do the separate classifier, well, I think that the only way to know is to try both approaches and see which one works best in your specific scenario. I would say the function calling is much easier because it also handles the extraction of arguments from the natural language. If you do the classifier, then you like pass it to different prompts, different LLMs, so that can become too messy and too many LLM calls. So I think function calling is a really good mechanism, but you should not overuse it, because if you start overusing it, it breaks down. Like once you have many functions.
Actually, I have, thank you for this part of the lecture, and I have a lot of questions about function calling. So you said that it was in the pre-training of the model. So the question is how is pre-training, and do we like produce functions on some programming language or some pseudocode or something like that, or we just classify and
so the function calling, yeah, thank you for the question. The function calling doesn't, well, the function call in the LLM doesn't execute any code. So it just tells you, we tell the model, you have a certain tool, you can use it if you want. And then if it wants to use the tool, it comes back to us and says, okay, I want to use the tool, instead of giving the answer immediately. So how is it trained to do function calling? In the pre-training phase, like the model is first pre-trained on the corpus of text and then on specific examples, and there are a lot of specific constructed examples when there are functions provided and the model either calls them or not.
So in the pre-training we give the function and the arguments and ask use it.
Yes,
like
exactly.
Okay.
So we give function, we give the arguments, we give the input message. Like for example, we say you have the function to call the weather and to calculate the currency pricing, and the user wants to know what's the weather in London. You should return function call. The function is this one, arguments are those.
And one more question, do we need to fine-tune this model to work with other functions? Or we just...
We don't. No, we don't. I mean, the function calling is built into most of the modern LLMs. Like most of the modern LLMs, meaning like Llama 3.4 and Yandex GPT-5, and when they can handle function calling. If they cannot, I mean, there is nothing we can do. We
So
can put the classifier at the beginning
in
instead.
the pre-training and in the usage of our LLM, we just pass the name of function and its arguments and something like that, and what it produces.
Yes, that is the functionality supported by the LLM. It should explicitly support function calling. If it doesn't, you
Okay,
can't use
thank
that.
you.
Okay, now we can put it, yeah.
Okay, thank you. In your presentation, you, I think, mentioned about like the hybrid search as an optimal retrieval, right? So, how can we, what do you call it, address the challenges of maybe if there is a, what do you call it, user input with both a bit vague and a keyword-centric, what do you call it, retrieval?
Yeah, I will talk a little bit later on about assessing the LLMs. So in short, we need to set up kind of testing loop when we have a set of questions and which we can evaluate. And then we can adjust the parameters of the retrieval and see if the result improves or not. So in practice, if you want to build a really good system, you need to do some kind of optimization, manual optimization of the retrieval.
Okay, thank you.
And prompts as well. Okay, let me
Question.
like only if you really want to, because I have a lot of interesting things to say. That was my mistake to open for questions.
Thank you for first part of lecture. Have you ever had experience in creation of a data set for evaluation of function calling, and which accuracy you get in a really practice case?
The answer is no, I do not have any specific example to share. The accuracy of function calling, from my experience, is definitely far from 100%. So sometimes it doesn't happen. And we can adjust, we can increase that accuracy by playing with prompt engineering and like doing some kind of tricks to improve it. But that is probabilistic thing, like sometimes it just doesn't happen.
Okay, thank you.
Yeah. Okay, so the title of the talk, by the way, is multi-agent systems. We should have time to get to them. So here, essentially, I put all that large pieces of code that I showed you previously into one big class, which allows me to create an assistant or an agent, I would call it, and pass all the functions, all the documents, everything I want to this agent. So I will, to simplify function calling, I would put the function to process the result also into the same class. So there would be class with the, there would be class with the field. Something strange is happening with my notebook. There would be class with the field. Here, so the class with the fields, and then the function to find wines. And I would also put one more function to hand over to give the control to the operator. So suppose if it's a wine shop, I look for some kind of wine, and then I say I want an operator to finish the process of buying it. And that would be a very simple function which just sets the global variable handover to true. So now I will, let's play a little bit with those things. I would create one more time an agent with this food wine table. And I would create another agent which would be the buyer, and I would just provide an instruction. You are a normal person who wants to buy some wine, ask like what they can recommend, and transfer to operator to finish the order. And what I want to do, I want to have those two talk to each other, right? That would be a nice way to test it, because instead of like testing it manually, I can test two agents against each other. So the seller says hello, well, that's actually me saying hello, but the buyer says, hello, I'm here to pick up a bottle of wine for dinner. The seller says which kind of dishes you are planning to serve with it. And then the buyer says something, and then there are two functions that the LLM wants to run at once, and the code breaks. That can happen. I will just run it one more time, hoping that it doesn't happen. No, it does happen. Actually, it happens because I did not create a new thread. Anyway, so let me skip this for the moment, just to save time. But you can play with it. You have the code, and those two agents, they can talk to each other, and there can be some interesting conversations between those. Why it happens that two function calls fail? I don't know, because I think the way I provide the result is designed in such a way that it should call it only once. Anyway, so that was an example of two assistants talking to each other, and that is not very interesting because, well, it is quite useful for testing, but in practice, like multi-agent system is much more than that. Multi-agent system is when we want different agents to work together on solving certain difficult problem. So you have heard probably that multi-agent systems, they are like the most important thing which would happen to AI in 2025. A lot of newspapers printed something like that in the beginning of the year when people asked like what would happen this year, and everybody said multi-agent systems. It's interesting that multi-agent systems, they appeared quite a long time ago, in 90s. I actually started my career in AI exactly like in 1995, and my PhD was about creating an alternative approach to multi-agent systems, alternative approach to knowledge sharing in distributed environments. So multi-agent systems, they had several motivations, like why they appeared. Like first motivation is like if we can create systems which is intelligent but not very intelligent, and if we put different systems together, we can maybe achieve higher level of intelligence. That is the hope provided by, there is this area of philosophy called evolutionary cybernetics, pioneered by Valentin Turchin, the Russian mathematician who invented the Rafal programming language and who later immigrated to US and continued his work there. So he published the book called I don't actually quite remember the name of the book, but so the book was about how everything works, and the main idea there is the principle of meta-system transition, that if you put smaller elements of the system together, there appears some kind of new capability of the system, higher level of control. Like if you put atoms together, there are not too many atoms in the universe, like around us we have something like 30 maybe different elements, but if we put them together we have molecules which are much richer than original elements. And if you put molecules together like DNA molecules, we get cells, and cells, they can be very clever, like amoebas. They can go where there is light and where there are better conditions, and then if you put cells together into organs and then assemble organs into a human being becomes alive suddenly. So there is a new kind of emergent level of control appears. And the idea is that agents, when you build system from multiple simple agents, there could be some kind of new level of intelligence. That was the first motivation. Second motivation was World Wide Web. World Wide Web appeared in 1991, and by the middle of 90s it was clear that we need to do something about searching and about using this distributed environment in a convenient way. So the people wanted to have like agents which would be able to find them information and to solve specific problems. Like I want the agent to book me a holiday somewhere when there is sea for 10 days, which is cheapest, and I have like this period available. And we want this system to be able to automatically do a certain number of tasks. So the guy who invented World Wide Web, Tim Berners-Lee, he started talking about semantic web, about the way to put into the web kind of structured knowledge which agents would be able to use and solve some problems instead of people. And Tim Berners-Lee predicted that in 10 years it would be like very successful and web would be navigated by agents more than by people. But it didn't happen. Why it didn't happen? Because like people are lazy. Nobody wants to put knowledge into the web in the structured way. We just want to throw a bunch of text and have Google find it for us, right? So that didn't work because of the laziness. And then there was a third motivation, like suppose you need to build the control system for the large plant, production plant. If it is a centralized system, if one thing breaks, everything breaks, and that's not good. And if we create a system by cooperation of independent agents, like each agent can control a certain part of the plant, it can handle problems if something happens locally, and it can also communicate with others to say, okay, here I have this problem, please like expect problems down the line. That can result in the very robust system. So there were projects like that, there was a project, interesting project about intercepting hacker attacks in the corporate network. Like a hacker attack comes into one host, we need to act locally fast, but we need to inform other hosts that something bad is happening here so they can act. So those kind of architectures started to appear, and as a result, there was a lot of attention driven into this multi-agent theory, and there was a book, Artificial Intelligence, A Modern Approach. It is like the most used AI textbook in the world, and in 1995 was the first edition, and you see after introduction, the chapter 2 is Intelligent Agents. The whole book was structured around agents and agentic theories. So the agents in 1990X, they were like autonomous entities which possess certain properties. Like agents are reactive, they can react to changes in the environment. They are proactive, they want to achieve certain goals, we set them goals and they want to achieve it. And they are social, they communicate. And there are a lot of theory have been put at that time into the communication, how they would communicate, what are the different actions that they can ask each other to do. There is the so-called communication act theory, which comes from linguistics, which was employed here to develop specific languages for inter-agent communications. And of course, a lot of efforts were put into knowledge representation, how to, because if the agents need to talk to each other, they need to speak the same language. So we need a way to define an ontology, a common vocabulary, a common properties for that vocabulary for a certain domain. And that took a lot of efforts. So that's why multi-agent systems in 90s, they were used, but not as much. So they exchanged specific languages like QML. They required ontologies to work. What has changed since then? Nowadays we have LLMs. So LLMs, first of all, they can communicate in natural language. We don't need specific languages to represent knowledge in communication. And they have some kind of internal ontology because they have been trained on the more or less same corpuses of text. They know things about the real world. Like we don't need to explain them things. So that's why it becomes much easier to build multi-agent systems, and that's why nowadays is a kind of renaissance of that theory which has been invented in the mid-90s. So let's again continue with the example of food-wine pairing. Suppose I have a difficult task. I want to suggest a meal for a person. The person comes to a restaurant and wants to eat. I need to suggest him a meal, main course and the corresponding wine. And I want to do it in the multi-agent way. Of course, this is a little bit simplified example. In the real world, probably the multi-agent systems would do something a little bit more meaningful, because this problem can be achieved by having just like one LLM. But in the real world, for example, if you want to have the system give you medical diagnosis, right? You can very well consider like a system which would act like in the real hospital. The person would be first interviewed by a therapist. The therapist would then send you to a number of specialists. Specialists would talk to each other, trying to figure out the diagnosis. Then somebody would check if the diagnosis is right and if it requires certain kind of improvement and more discussions, and then it will be given back to the original person. So those kind of systems, they achieve much better results than if we were using just one LLM. So in our case, we have different roles. We have first of all the visitor who wants to eat. We have the waiter who knows the menu, and we have sommelier who knows the food wine matching. Normally, for building those kind of systems, there is a library called LangGraph, which is built on top of LangChain. LangChain, you already have heard about LangChain today. It's a very good framework for building systems around LLMs and vector knowledge bases. And LangGraph builds the multi-agent communication layer on top of that. So we will instead use the same LangGraph to build the communication layer on top of the assistant which we have already developed on top of Yandex Assistant API. So how would that work? We have the visitor, first of all, express what he wants to a hostess. A hostess extracts his initial wishes, like if the person says, I want to eat some fish, the hostess says like his food preferences is fish. Then there would be a dispatcher which communicates either to waiter or to a sommelier to do food wine pairing. And LangGraph, it is called LangGraph because the central concept there is the communication graph, which passes the state of the system between different nodes. So there would be this state of the system passing through different nodes. So the state of the system would look like that. For example, in my message, I say, I want steak. Then somebody extracts the, this hostess extracts the food preference, steak. And then waiter says, okay, for the steak I can recommend filet mignon. So those agents would act in turn in reaching the state, like changing the state. And then depending on the state, it would figure out what to do next. So this would be this kind of graph. We come in with the message, I want steak, then extract the food preference, then waiter decides what would be the main course. Then we do the food wine pairing. For filet mignon, we recommend some kind of Merlot wine. We ask the waiter again, like which kinds of Merlot is available. It gives us the specific type of Merlot, and then we give this back to the user. So that is we want to now reproduce. So first of all, different agents. To call different agents, we already have developed everything we need. We says waiter is an agent which has the access to the menu. So I provide menu as RAG content to it, and I provide the instructions that you are a waiter, your goal is recommend food to visitors, and you know the menu. So now let me check this. I say how much is the ice cream. It tells me that there is no ice cream in the menu, hopefully, because there is no ice cream in the menu. So the menu does not provide the price for ice cream separately. However, the chocolate apocalypse dessert includes ice cream. Good. What is the most expensive wine? And maybe it will figure it out. Okay. Now, sommelier does food wine pairing. For food wine pairing, I give him the table which we have previously put into a number of documents. So this docs is the list of the chunks of the table with food wine pairing. So now I can ask this agent which wine would be good for steak, and it would tell me. And the hostess agent is a little bit tricky. I want to extract very specific fields from my input prompt. If I want to extract specific fields, I have one feature of large language model called structured output. So previously, like if you wanted the model to output some kind of structure like JSON, you had the problem, because you can ask the model, please give me JSON as the result, but you had no guarantee that it would give you JSON, right? It can tell you the result is and then JSON. It can sometimes just give you JSON which doesn't which is not syntactically correct. But structured output is when you provide the schema of the output to the generator. And because generator works by sampling probabilities of the next world. So this generator can check if it conforms to the grammar, it would just ignore all the words which do not conform to the grammar. So it would exclude the possibility that the result is not syntactically correct, right? So this structured output is a very powerful technique. You give to the model the schema. In this Yandex Cloud ML SDK, the schema can be again figured out from the Agentic class. This is very convenient because writing JSON schema by hand is a hell. I mean, like, it's very unpleasant thing to do. Here it does it for you. It just says, I want the result to look like this: food preference and wine preference. And this hostess agent, just please give me person preference as the result. So I run it. I want to eat something from meat. It gives me this object: person preference, food preference, meat, wine preference, empty. Again, structured output should be supported by, well, not probably exactly the model, because you don't have to train the model to do the structured output, but by some kind of tooling. So now let me put all that into this big graph, agent graph. So the state would be the following. It would contain the original message. It would contain the communication thread in which all agents would talk to each other. Then food preference, wine preference are the original preferences. Then main dish and wine are the food which has been selected from the menu for the final dinner. And answer would be the textual answer to the user. Now, the graph in LangGraph is defined by a number of functions. So each node of the graph is a function. So for example, welcome user, it's the first function which works. So it receives the state. I take the message from that state. I run the hostess agent to figure out the preferences, and I return those preferences as the update to the state. So this function should return the update to the state, not the new state, but the update. Why? The library has been designed in such a way. Then, so there are a lot other functions for other parts of the graph as well. Then I need to define this graph explicitly. In LangGraph, I say here is the graph based on this recommender state. There are following nodes: welcome user and others. Then I want to add the edges. From start, I go to welcome node. From welcome node, I go to clarify node. From clarify node, I call the function root user, and depending on the output of this, I go to different nodes. Right? So this is how I define the graph. I define the graph, and I can even display this graph, but not here, because here I don't have access. Internet doesn't allow me to go to the Mermaid server, which would render it beautifully. But this graph has been generated from Python code. Well, not exactly this, but the one very similar to this. Okay, now I have compiled this graph. So what else? I would not probably go into detail, but I have already described how this works. I have a lot of printing here so that we can actually trace how the selection takes place. Now, to run this, I say I want to invoke the compiled graph with this message: hello, I want something from meat. And I create a new thread for communication. And I run this. And then the magic happens. So initial message, I want something from meat. Preferences, food preference, meat, wine preference, none. Then clarify says, looking for the food in menu. So I ask the waiter to look for the menu which matches meat. It gives me ball on edge steak. And then I want to recommend the wine for this. Then I want to look for specific wine. And then I find the Final answer. So this would be the final answer. Ballon aged steak with Merlot by Marchesi Antinori, Italy. It's interesting that my talk is before lunch, right? So we can get prepared for lunch. We can also have a look now. We have the thread of communication between agents. We can see how they talk to each other to figure out the answer. They actually talk to each other in natural language. You see, the user asks which of the dishes in the menu correspond to the following description: meat. And the assistant says ballon aged steak. Which of the wines would be good for dish? This is the question to sommelier. So it gives the answer. So those agents, they communicate in one conversation thread. Now, what if the user wants a bad combination? Say, I want some fish with Merlot. This is horrible. Red wine with fish. So it figures out first so it looks like for the wine in the menu. First of all, it figures the wine. Then it looks for the menu for the fish. It figures out the dish. And then it checks combination and says, oh no, you should not order that. I'm sorry to inform you that salmon, dreaming of Norway, and Merlot don't go well together. So that is another case. One more case. I want something good to eat. So in case I want something good to eat, there is a separate node in the graph for that. And the random dish is selected. So we ask the waiter to select the random dish of the day. So that is how this system works. Let me see if I have some beautiful slides. Yes. So this system, you can see that it's kind of the communication between agents is a kind of hard-coded one, right? We define explicitly the graph, which is, in a way, it's good because we control what happens. Nothing can go wrong because we can only go by from one node of the graph to another. It is still not static, like it's not the predefined path, right? The path depends on the state. So we can handle different situations. Like in the case of medical diagnosis scenario, we can have different doctors and then therapist decides to which doctors we go, and like it's still dynamic, but the communication between agents, it's kind of predefined. So Anthropic released about several months ago a guide building effective agents. And Anthropic calls this agentic workflow patterns, agentic workflow. So it's not like pure multi-agent system, it's agentic workflow. And in that paper, they define different possible patterns, like this one probably was, the one that we used was similar to supervisor. There's been one central node which kind of decides what to do next. There could be like hierarchical patterns, like a node decides that we need to give this entirely to new subgraph, and that subgraph does something and comes back to us with an answer, and then we take this answer and then we do something else. So hierarchical is good because we can build really complex systems, right? And also, like in practice, multi-agent systems are good when we also have organizational boundaries. Like there was one interesting case from Sberbank. I think they, I don't remember what they did, but I remember that they had different completely different organizational parts of organization responsible for different parts of information workflow. And multi-agent systems are very good for that because you can give like one organization complete responsibility over like what they do, and it's very well decomposable. But yeah, let me also speak a little bit about testing this. So if we want to test something like natural language systems, it's a little bit tricky because like they give natural language answer. How do we verify that the natural language answer is good? There could be several ways. You can either compare it to some predefined answer using embeddings, how similar it is, for example. Or you can try LLM as a judge. You can say, you can ask another LLM, like, is this a good answer or not? Or you can define some your own criteria. You can say, for example, in our case, it should not like give answers like meat with white wine and so on. We want to check that. So for testing LLMs, also one more tricky thing is that for RAG systems, it's important sometimes to test retrieval separately. Like you want to, if the RAG gives you bad answer, you need to know what is the problem. Retrieval problem, the good answer didn't make it to the retrieved chunks of content. Or the LLM, which figures out the answer, is problematic. So for that, there is a special framework called RAGAS. RAGAS is it's like not the only one, but it's a very convenient one to use. And I will show you an example. So for that, I will prepare the data set of 3 questions, which we have seen before. I want to eat something from meat. I prefer fish. I want to eat salmon with red wine. And reference answers. Reference answers are the ones which we would expect, which we would say are good. And I can run our system against all those examples. I will not do that to save time. I will just load. Let me actually here. I would restart my environment to start from scratch, and I would load the same table, the same JSON file, but with provided response. So response is the ideal response from the system. Well, not ideal, it's response from our system. Now, how can we measure similarity? I say, okay, I want to use embeddings. Embeddings can also be used in the cloud, like Yandex embeddings. And I have this evaluation data set from those 3 examples. I constructed from those 3 examples. And I say evaluate those tests on answer similarity metrics based on those embeddings. So what RAGAS does, it goes through all the samples. It will start doing that in a moment, hopefully. And it would evaluate answer similarity for each one and give me the final score, 0.75. Is it good or not? Well, nobody knows, but probably it's closer to 1 than to 0. Probably it's not too bad. The good thing is that once we have this metric established, we can go back, fine-tune something in the system and measure it again. Once we have something measurable, we can optimize that. That is what I answered, I think, in the first Q&A session. More interesting things, we can develop our own metrics here. We can say, for example, does the recommended wine match the recommended main dish well? White wines go well with fish, red wines with meat dishes. If the food and wine do not match, it should be explicitly indicated in the answer. So I provide my own prompt, and I say I want this aspect critic metric, food wine match, based on this prompt, using this LLM as a judge. And I would also use another answer accuracy, another predefined LLM as a judge metric. So now I can run this. And it gives me perfect, not perfect, what's wrong? Wood wine match, 0.667. No, too bad. I want 1. Yesterday I had 1. Now I have 1. Good. You see, you just need to run it again. Well, actually, it's a very good demonstration that LLM is a highly probabilistic thing, right? So if you're using LLM as a judge, sometimes it can judge wrongly. Which one it judged wrongly, we don't know, but yeah. So that was agentic workflows. But there is also another possible approach to doing multi-agent systems, which is, this is Russian, you shouldn't see that. This is English version. So another approach is the following. Let us just build an agent which we will provide different tools and let it decide automatically which tools it wants to use. And not only tools, but sometimes if you want to delegate this to another agent, let him do so. So this approach is implemented in the library called Small Agents. It's a library developed by Hugging Face. And Hugging Face, by the way, had a course on multi-agent systems about several months ago, I think it ran. I cannot personally recommend it too much, but if you want to kind of delve into this topic a little bit more, it contains also sample notebooks which you can just go through and see by yourself. So this small agent, the idea of small agent is that you write an agent which can write code in Python. So the agent runs arbitrary code, then it executes this code, it does something, the agent looks at what it did and decides what to do next. So LLM is responsible for figuring out each step of the scenario by itself, right? So how does this look like? Well, we can use here, we will use the small agents also with Yandex GPT, but this time we will use Yandex GPT as an OpenAI compatible endpoint. So I basically specify this endpoint, I say OpenAI server model, but as an endpoint I specify the model inside the Yandex Cloud. It's Yandex GPT, I can also specify Llama, I can specify Qwen. So for the first example, I will give an agent an ability to search internet. This small agent has built-in DuckDuckGo search, but we don't know if DuckDuckGo search would work here, so that's why I created my own Yandex search tool, which basically goes so what's wrong here? Why search? I have lost a piece of code. Too bad. Let me try DuckDuckGo search instead. Oops. DuckDuckGo search tool. So I want to say how much a meal would cost in Harbin. So what it does, it says I want to do a web search on cost of meal with good beer. For some reason I decided to switch from wine to beer. Rate limit. Step 2. In this case it decided, you see it's different code, it decided to break this into 2 web searches. Like if there is a rate limit, why don't I do 2 searches instead of 1? That's a very smart idea of the LLM, but it gives some results. Here you have the results. And then step 3, the agent provides the final answer. A meal at an inexpensive restaurant would cost 20-30 yen. So you see, very clever agent. Even though the search didn't work, it didn't stop, it persisted and found us the answer. So good. Now let's see if we can use this for our case scenario. If I want to construct a meal of 2 courses in the restaurant. How would I provide the menu of the restaurant? The very good way to do that is so-called model context protocol. I don't know if you have heard about model context protocol. It's essentially a way to do a distributed RAG. So in RAG you give documents to the agent, and you provide, like if there are functions, you provide those functions. MCP, Model Context Protocol, allows you to specify remote functions and remote documents which would be used by an LLM agent. So LLM agent would go to that MCP, do a remote call, ask which functions are available, get back the descriptions of those functions, integrate them into LLM, and when LLM wants to call the function, it would call the function over the network. So that sounds exciting. What you need to do to implement it is essentially implement an MCP server. So the restaurant would provide an MCP server giving the menu. It's very easy to do, like there is an excellent Python tooling for that. So an MCP server would look like this. You see a like 1 page of code. I would decorate every function by mcp.tool, and I would have the tool get food menu and get drinks menu. I provide typing here, that's important, and I provide the description here, that's also extremely important, because this description goes to LLM. How does LLM know which function to call? We give it this description, like what this function does. So that's why we need to provide this description. And then that's basically it. I return the menu. So very simple code. And here I start this server separately in the shell in my local environment. Of course, I can do it remotely on some server, but in this case, it's done locally. And to use this MCP, I say I want to use MCP client on my local machine as tools, and I would send those tools to my coding agent. And I ask which is the most expensive dish. So let's see what it does. In step 1, it decides to get the food menu. This is the food menu. And then it says, okay, the final answer is ball on edge steak. So what it does, I mean, LLM looks at this code, right, and figures out the most expensive dish. Sometimes it does better than this. Let's try it once more. Sometimes it writes Python code to actually go through the table and figure out the most expensive dish by the code. But this time it doesn't want to do that. Anyway. So that's as easy as that. Now we know how to get the menu from the restaurant, and we need to figure out with food wine pairing. How do we do that? Well, we can also implement that as separate tooling functions, right? So for that, I would get the food wine table into the data frame, and I would compute the embeddings for food and for wine columns, right? For each column, I would provide an embedding, food embed and wine embed. I will not run this because it takes a few minutes. I would read the already pickled table. And based on that, I would create the function, find matching food and find matching wine. Let me run this. So that's a very easy function, like we embed the query, we find the closest columns for that, and that's it. So for dry red wine, spicy lamb, meat ravioli, and then define matching wine, the same. Here again, it's very important to do the annotations because it's a tool, and LLM would know when to call a tool by looking at the description, at the comments. And now what I do, I said I want a code agent. I want to give it my tools from the MCP plus those two functions, find matching food, find matching wine. And I say prepare a menu for dinner, which consists of main course, matching wine, and the dessert. Provide the result as a table of the name and price, and calculate the total price. Let's see how the agent does. So first it gets the menu, it gets the drinks. Then it encodes the price, calculates the total price, and gives me the answer. So it looks quite nice. The question is, of course, like which approach is better. Yeah, again, how this works, we start with a query. We ask LLM, you have this problem, please decompose it into parts and say which part to do next. So this is the thinking phase. Then the act, we execute the code. We get the result. So this is observation. And then the LLM looks at this result, and we say, please look at this result. Look at the original plan, revise the plan, and tell us what is the next step. And then it goes in the loop until the result is obtained. So this is called React Agent, Reason and Act. React stands for Reason and Act. There could be, it doesn't mean that multi-agent system should have only one agent like this. It can have several agents, and it can delegate, for example. We can say that the visitor comes to the planning agent, and then it would delegate the functions to different other agents as well. So it's possible to build some structures in this manner two. So which one is better? It depends on the problem. So if you are in a production environment, you want to build an assistant which would provide the answer to the user in the timely manner, which would not spend a lot of money, probably you would go with explicit agentic workflow. Because it is controllable, you would know more or less how much it would spend, and you would know how much it would run. It would finish, hopefully after more or less understandable number of steps. So if in production environment, most of the companies nowadays go with the agentic workflow. If you want to do kind of research problem, if you want to search what is the cheapest meal in Harbin, or you want to like build a report on current state of multi-agent systems in 2025, or you have the database of clients you want to like build the report on them, then this approach with dynamic code generation would work well, because you don't need the result for sure. Like if it breaks, you just run it again and see how it works. So this approach is very similar to what OpenAI does in deep research, right? So it does pretty much the same thing. And the result can be good, the result can be bad, but you would get something. This, of course, spends a lot of LLM tokens. Because in the agent, you can imagine like each run of the React loop produces code output, and this code output is stored in the conversation. And all that is put into the next phase of the LLM. So LLM always works with a lot of tokens. And big context is quite important there. So there are presently those kind of two approaches. There could be something in between, because in lang graph you can build React agents as smaller subcomponents, and in React agents you can trigger workflows, so you can of course take good and bad things from both worlds. But in principle there are those two ends of the spectrum. There are also different frameworks, like Microsoft AutoGen framework, for example, is similar to small agents. It's more flexible. LangGraph, Llama Index, they are more oriented towards agentic workflows. So that was the main, I think, idea of this talk, that currently when you say multi-agent system, different people mean different things. And people are trying to figure out where it's best to use them and how. It's not always an easy and obvious that you need to build multi-agent systems, because like LLM, as far as LLMs are concerned, like LLMs are, when LLM replaces a human, it's almost certainly much cheaper than a human being. Right? When a multi-agent system replaces a human, like if you want a system which gives you medical diagnosis by doing the consultation with a bunch of virtual doctors, it's not obvious that that would be cheaper than actual human, because it would cost a lot of LLM tokens. And that's why like we need to make sure that it's feasible. It's not always economically feasible, so that's why currently multi-agent systems, they are on the edge of being explored for potential use in the industry. Okay, a few words also from our sponsor. So Yandex, who provided you generously with the Yandex Cloud, which you can use for your projects here. Yandex does, like for example, this is done as part of the Yandex Social Projects, which is a special division which works to bring together students, different non-governmental organizations, cultural institutions, together to solve important problems. And we try to do it on the periodic manner. So there have been a lot of projects done, for example, with museums, with resorts, on tracking animals, with ecological organizations. And so we work together with students from leading universities on those projects. So if you want to learn more about that, there is a Telegram channel and website for that, and you are welcome to learn more and take part if you want to. Any questions? That is my Telegram channel if you want to learn more about what I am doing. Any questions?
Thank you for the presentation.
Thank you for the presentation.
Thank you.
What did you say? Well, there are two approaches. You can combine everything in one agent, or you can use multi-agent system. What would you say is the optimal, I don't know, like some criteria for where you need to use many agents already because one agent is not enough? What are indications of that?
I think like the best way is to try, because like sometimes when you just use one LLM, when you use multiple LLMs instead of one, you just you get better quality at the end, because each LLM has different system prompt. They can look at the different aspects of the problem. You can model that with one LLM, of course, like you can, for example, change the prompt and say, look at this aspect of the problem, look at the other aspect of the problem. That's what many people do when they use ChatGPT, right, manually. They say, please consider this problem from different sides. And multi-agent system, like one of the way to look at it is this kind of looking at the problem from different angles. We can just call it different agents communicating with each other. That is like easier from the software point of view than having different prompts in the one long conversation. Also cheaper probably, because in one long conversation you always put this conversation into LLM, and if you just pass it through different system prompt plus the problem, it is like shorter amount of tokens. So
Maybe in terms of modularity or like, for example,
so like one probably scenario is when you have those kind of very different specialists in real life. You can model that with the multi-agency. Another case is when you have complex organization and you want like different parts of organization to be responsible for its own kind of execution agent. And then you can just define the protocols to exchange information, and you don't have to, like, you delegate the responsibility further. That is the case of like Sberbank, which I tried to mention. And the third can be like the complexity of the problem, because if the problem becomes too complex, it's easier to think about it in terms of like delegating it to like sub-agents, and then you design that to solve like simple sub-problem. So it's also a kind of way to structure the system itself. So it maybe consider it as a design pattern for software development, if you will.
Thank you for the lecture. Can you please repeat what is the MCP is for?
Yes, Model Context Protocol is the protocol for providing tools and content for the assistant in a remote manner. So
what does it mean?
What does it mean? For example, you have a tool which can give you a weather worldwide, for example. If you want to connect it to an LLM so that LLM can use it. For example, if you want to be able in ChatGPT ask what is the weather in Paris and give you the answer. You can provide the MCP server if the like ChatGPT environment supports that. I think it should. You provide the MCP server, and it goes there. It asks like which functions are available and integrates them into the LLM. So LLM knows that it can call those functions when needed. And then when you ask what is the weather in Paris, it calls the remote server, gives you the answer, puts it into LLM, and gives it back to the user.
But you mentioned, like, for example, DuckDuckGo, and you used it before MCP. How is that different?
I used what before?
The browser, DuckDuckGo, I guess.
Well, yeah, because that was like the DuckDuckGo. It was the function which I provide locally. So MCP is basically a remote way to provide the function, like do remote call with a distant server.
And you use DuckDuckGo from the local server.
Yes. Well, yeah, I call DuckDuckGo.
So why would I need
What
to
is the
use
difference?
MCP if I can use local server?
The MCP is the standard protocol. So I don't have to hard code it. In the case of DuckDuckGo, the code was hard coded into this library, small agents. In case of MCP, it's universal protocol. I just say, here is the server with functions, and I can implement functions there in any language.
So apart from implementing a function to search in DuckDuckGo, I have to implement a protocol also?
No, you don't. Like the framework implements the protocol. You say, so essentially it's a way to tell this is the remote server which provides this functionality. And that's it. And this model context protocol, it's pioneered by Anthropic. It is supported not only by this framework, but also by some others. So it's kind of cross framework way to say I have some tools for LLM to use.
So if I have a local tool, I can't use it with like ChatGPT. And
if you what?
So MCP is the only way to use tools with some API models like ChatGPT.
It's not the only way to use tools with the API models. With API models, you can pass like your own tools, like I showed before. Today, I used always the API models, but it's the only way to use tools with closed. For example, like if you use Cursor AI IDE for coding, right? In Cursor AI, you can put MCP servers, and it can use external MCP servers, which would give additional information about the code. And like this is a standard way to do it. Like you cannot go and code anything inside Cursor AI, but you can say, here is my MCP server.
Okay, thank you.
Think about it like a higher level of REST protocol. So it's REST protocol plus some kind of extra additional functionality to provide function descriptions.
Thank you for the lecture. Could you please tell how LLMs are trained to use tools?
How LLMs are trained to use tools is basically by giving them samples which use tools. So for example, we give LLM the text which says, like the user question is, please give me the weather in Paris, tool list, like determining the weather, and the function that LLM should return, please call the tool, like the status, like tool, call the tool, arguments, location Paris, and that's it. We provide a lot of examples like that, and LLM learns to figure out like when to use tools. Because to use a tool, what it needs to do, it needs to match the tool description with the user prompt somehow.
So it's like supervised fine-tuning or some reinforcement?
It is done as part of supervised fine-tuning, I think.
Thank you.
But you can imagine that it's very easy to generate a large data set for that, because the data set can be generated like almost automatically.
Hello, thank you for your lecture. It was pretty good from one point of view. Well, my question is, from my experience, the multi-agent systems is pretty complex systems. If we want to solve some really complex tasks, we're really unstable without strict rails when they use lang graph or lang chain. So can you please maybe elaborate how we can, the perspectives of these multi-agent systems when they solve really complex tasks, which requires not just tool calling, but also reasoning, I mean long-term planning, etc., because I don't know how to stabilize them, because the prompt usually does not work really good, and on your slides there was a problem with the scores. You just need to run them 2 times. They're undeterministic. And maybe you can also elaborate some examples of use cases in the production line of the multi-agent systems, because right now I know they are pretty scientific point of interest.
Yeah. thank you for the question. I like the word stabilize. And by the way, one good way to stabilize the problem with my slides is to run it 10 times and then average over. The good thing is that some architectures of multi-agent systems, they can stabilize themselves. Like, for example, this React approach. You see, like, it generates the code. If there is an error in the code, it just, generates a new one. It gets the error message and it corrects the code. So in a way, this approach can act as the stabilizing component. Instead of, like, when the system becomes more complex, instead of getting less robust, it becomes actually more robust. In terms of real-world scenarios, as I mentioned, there are very different things we mean by multi-agent systems. And for example, one of the things is like this React approach is used nowadays quite commonly in the coding assistance. In the cursor AI that I mentioned, you can say, please write me something. And then it does exactly this. It does planning, and then it does code generation, it revises it, and gives you the final result. So this is an example where multi-agency is used a lot. Like maybe, I mean, it's of course the question whether to call it multi-agent or single agent, but at least it's an agent system. It's the system with this React loop. For largest scenarios, I would agree it's more on the experimental phase right now. So there are not too many industrial examples which we can share of that.
Yeah, thank you for your lecture. Could you comment on the quality measurements of such agents framework, especially multi-agent, and that's it.
I think the quality measurements would more depend on the problem, because it's how well we solve the problem.
But maybe there is some qualities. For example, all RAG applications have almost the same quality measurements, and they are independent of the problem.
Which you mean retrieval accuracy or things like that?
Yeah, that's it.
I probably would say it's not obvious to me which could be such quality measurements, because I think in multi-agent system, as I mentioned, there are different designs. In RAG, those quality metrics depend on the design, because we have retrieval, we have the post-retrieval part, right? And we can measure separately those two components. In multi-agent systems, we can, if you have several agents, we can imagine that you can measure quantities like quality, you can measure qualities of both, of any agent separately somehow, but that would depend on the design. So I cannot name universal.
Okay, thank you. And one more question, please. Do you know some playgrounds or sandboxes for the agents just to test before the usage in practice?
Sandboxes, if you mean like code generating agents like I showed, they try to run the code always in some kind of sandboxed environment. And I don't quite remember the name of the library, but I think the small agents uses some kind of an extra library which exactly does this sandboxing. And there was a startup which also does that, but which I forgot the name of. But that is with code generation agents, that's a popular problem, how to isolate it from doing something harmful.
Okay, thank you.
Any questions?
Thank you for your lecture. Could you please explain one more time about function calling? How can we announce all available functions to the model? Yes.
We do it if we are talking about API models. In the API, there is a separate kind of field which you provide, tools, and then you describe which tools are available using some kind of JSON schema. In case, if you go low level, to the model itself, it's built into the template, because the model converts this original JSON into some kind of template which it passes directly to the model. So there is a piece on this template exactly for those functions.
So is it something like a part of a system prompt or something?
It's not a system prompt, because system prompt is in the beginning of the conversation. This is the part of every conversation in turn.
Thank you.
But it's a part of the message.
Okay, let us thank our speaker.
Thank you.